Good morning. We will continue with our subject on solid propellant rockets. What is it we have done so far? Let us take a quick review. We know that whether the propellant is composite, whether it is double base, or it could be nitroamine, or it could be composite modified double base. I can write the burn rate as a linear regression rate, R is equal to AP to the power n. We also told ourselves that, well, if I have a rocket in which the burn surface area is SB, the equilibrium value of pressure I can derive as maybe the burning surface area into this particular exponent A. We had something like rho p here, we had C star here, divided by AT over here to the power 1 divided by 1 minus n. How did this come? We said if I have a rocket, let us say we considered a simple scheme wherein I had propellant which was enclosed in a case. I had something like a nozzle here. We said the rate at which mass leaves through the nozzle, m dot n, can be written as P AT divided by C star, where P is the pressure here, and we said it is always choked at the throat, therefore this is the volume I am considering, and that is the mass at which is leaving the nozzle, and the rate at which mass is getting generated from the burning of propellants. We got that as equal to the regression rate is R, and that was equal to SB into the propellant density into the burn rate R, which is equal to AP to the power n, so much kilograms per second. This is so much kilograms per second. We equated the two, and then we find I take P over here, I get 1 minus n, I get SB A rho P into C star divided by AT, and this is the equilibrium pressure. What does this tell us? Let us take a relook at this equation. We looked at it from the point of view of n, told ourselves, well, n cannot be anywhere near 1, because then what happens for any small change here, there is a large magnification here, and therefore n should be very much less than 1, because if n is near 1, I get a very large exponent here, and a small change can magnify into a large change in pressure. Therefore, we say from stable considerations, well, n must be very much less than 1. But we also learned to look at it graphically, and what did we tell at that point in time? When we have n in the burn rate equation, R is equal to AP to the power n. If n is greater than 1, how does the burn rate law change as pressure changes? Let us make a plot, or rather as burn rate increases, if you have a given burning surface area, a given density of propellant, we can now plot the rate at which mass gets generated due to burning. In other words, mass which gets generated depends on the burning surface area into the density of the propellant into the burn rate law. We want to plot it as a function of pressure. When n is greater than 1, well, it keeps increasing as n becomes greater and greater. Rather, when the value of n is greater than 1, when for large values of n, the mass generation rate rapidly increases. If, however, n is less than 1, like for instance in the burn rate law n is less than 1, then the same mass generation rate will have something like a drooping characteristic. This is for n less than 1 with variation of pressure. This is for n greater than 1. How does the mass flow rate which leaves the nozzle change with pressure? We always told, we have been writing this on and off, m dot is equal to 1 over C star into P into AT. Rather, the mass flow rate through the nozzle, if now I call it as m dot n through the nozzle with respect to pressure, will increase as a straight line. Therefore, let us now plot the mass which leaves the nozzle as a function of mass generation rate for n is greater than 1, n is less than 1, and see whether we can draw some conclusions on the type of exponent n which we require. Let me now plot all the three together on a single graph. Let me have my axis here, x axis, which is mass generation, or let us say mass which is leaving the nozzle as a function of pressure. Let me put the value first for n less than 1, I get a curve like this. If I have n greater than 1, let me title it, it is n less than 1. If I have n greater than 1, well, the curve is like this. And what is the rate at which mass is leaving the nozzle? I show it by a white line again, maybe the curve is like this. Now we find that for n which is greater than 1 and the mass which is leaving the nozzle, it is same at this point, therefore this will correspond to, let us say, equilibrium pressure for the case when n is less than 1. N is greater than 1, I am sorry, red line is for n greater than 1, therefore P equilibrium corresponding to, let us say, case 1. Let me also tell that maybe for n less than 1, maybe this is the P equilibrium value, let us say it is P equilibrium 2. I would like to examine whether are these two states which are possible. Well, theoretically this is the rate at which mass is leaving the nozzle, the rate at which mass is getting produced in the chamber, and therefore this is the equilibrium pressure. Similarly, for n less than 1, this is the pressure. Let us try to get some idea whether these states are possible, and if so, are there some problems in these equilibrium pressures. When n is greater than 1, let us say I have a small perturbation in pressure, a small perturbation can always come, and let us say that the pressure reaches this value. That means the pressure is slightly higher than the equilibrium value. Since the pressure is slightly higher, what we find at this point, the mass generation rate is higher than the mass which is leaving the nozzle, therefore pressure will further increase. When pressure further increases, the mass generation rate is further high increased, therefore this point cannot be a stable equilibrium point, but any small perturbation will make the pressure increase further and further till the motor sort of ruptures. If I now consider the points to the left of the equilibrium point, let me say that maybe by some chance there is a small pressure perturbation and the pressure in the motor falls to a value less than the equilibrium pressure PE1, then what happens? The mass generation rate is lower than the mass which is flowing through the nozzle. In other words, mass flowing out through the nozzle is more than what is generated, therefore the pressure still falls, the pressure still falls, pressure still falls, and it comes to extinction. Therefore we tell ourselves, well, in case n is greater than 1, I cannot really get an equilibrium pressure, and even if I get small changes in it will allow it either to explode or to quench. Therefore we tell ourselves n greater than 1 is not desirable or not possible. Let us examine the case when n, in the rate law, what was the burn rate law? R is equal to AP to the power n. What is the value for, what is the value when it is less than 1, what is the state of equilibrium pressure? Let us put the same arguments again. If the pressure were to fall slightly less than the equilibrium value, well, it has fallen, but now I find that the mass generation rate is higher than the mass which is leaving the nozzle, and therefore it will go back to this particular state. If by chance it exceeds the state over here and comes over here, again I find, well, the mass leaving the nozzle is higher than the mass generation rate and it pushes it back, therefore it pushes it back to this point, therefore this point becomes, let us say, a stable equilibrium value. Therefore the value of n less than 1 is possible, and it gives rise to what we say is a stable burning. Therefore in the burn rate law, R is equal to AP to the power n, n must always be less than 1. This is all what we have done. Now a time has come when we have to put everything together and say, how do I design a motor? What I mean when I want to design a rocket? I must be able to generate a given thrust from the rocket, and what is the thrust? We said is equal to Cf into P into AT. I dropped the subscript Pc because we said I can put it in terms of the nozzle effectiveness into chamber pressure in 80, this is the thrust which is developed. Therefore, if I want a rocket to develop a particular thrust, I know that P equilibrium goes as SB, all this is constant, rho P is density, C star is a particular case of a propellant, I can evaluate it, I know the throat area, all what I need to do is configure the surface area such that I need a particular thrust, and this is all a solid propellant rocket does. But it is not that easy, as we shall see in the subsequent class. When I go through it, you will find, yes, there is something much more to it. You know, I cannot just say, therefore I can write this equation as Cf into, I take the value of Pc from here, I can now write it as Sb to the power 1 over 1 minus n. What did I do? I take P equilibrium going as Sb to the power 1 minus n, therefore I write that here. Then I write the other terms together, namely I get AT. Now AT is in the numerator here, AT is in the denominator here, therefore 1 minus 1 by 1 minus n. I have just substituted the value of AT over here, minus 1 over 1 minus n, there I had it in the numerator, and then I soak the other parameters, namely A, the value of rho P into C star to the power 1 over 1 minus n, right. Therefore, you know, this is a constant, throat area is given. If I know the evolution of burning surface area as the surface regresses, I can find out the value of thrust, and that is how a solid motor is designed. It is a simple geometric problem. We must be able to calculate what must be the value of Sb and how Sb, the burning surface area in meter square, evolves with time, and this is what we will be considering in today's class. But before I do that, so far all what we have done is we took the burning rate law, R is equal to AP to the power n. We considered explicitly the effect of pressure alone, but we said A includes the effect of temperature, initial temperature of the propellant. Let us take an example. See, we can consider a temperature of the propellant to be ambient, that is, a rocket motor is tested today, the temperature is quite hot today, maybe 32 degrees centigrade. Well, you all would have learnt about a solid propellant rocket which misbehaved in space shuttle. It was a Challenger rocket which was launched on a very cold day when the temperature was around 0 degrees centigrade, and we will look at that failure after completing this portion on solid propellant rockets. That day was quite cold, around 0 degrees centigrade. Well, we could have a missile which is operated from mountainous area near Himalayas where the temperature could be as low as minus 50 degrees centigrade. What is the effect of burn rate on temperature, that is the initial temperature of the propellant itself? I am not looking at the flame temperature, all what I say is, well, I have a propellant block, the initial temperature of this block before it burns or just begins to burn is what I call as initial temperature, and here I have a flame and I am looking at the effect of initial temperature on the regression rate of this particular propellant. Maybe let us take a look at it, how I do this problem or how we can do it. We define a term known as temperature sensitivity factor. Let us see what it is. We would like to know how sensitive the burn rate is to temperature changes. Therefore, we were interested in finding out how the burn rate dr changes with temperature dt. And since I am considering the effect of temperature alone, I am considering at constant ambient pressure. Okay. But then instead of just saying burn rate variations with temperature or the variation in burn rate due to unit temperature, I now say fractional variation in burn rate, and this is known as pi r or temperature sensitivity factor for burning rate. In other words, we define a term like pi r is equal to this dr by r is d ln r divided by dt at constant pressure. is defined as the temperature sensitivity factor for a solid propellant. And just like how did we measure R is equal to AP to the power n? We did two experiments at pressures P1 and P2, measured the burn rate R1 and R2, and n was equal to the value ln R1 minus ln R2 divided by ln P1 minus ln P2, and the same way this is also measured at different temperatures, and typically the value of the factor pi r which defines the sensitivity to temperature is around 3 into 10 to the power minus 3. What should be the units? Well, ln r has no units, dr units cancel, it is only dt, therefore degree centigrade inverse. For 3 into 10 to the power 3 for typically for most composite propellants, this is equal to something like 5 into 10 to the power minus 3 degree centigrade for double base propellants, and for HMX based propellants it is even lower, it is 2 into 10 to the power minus 3. And that is why for missiles you go for HMX propellants because it is not that sensitive to variations in temperature. For degree centigrade inverse for HMX based or nitramine propellants. Well, I can go back and integrate this equation and find out explicitly how the burn rate changes with temperature. Let's do that. I take this expression over here, I write d ln r logarithm of burn rate is equal to pi r into dt at constant pressure. Okay. All I have taken is the change in the logarithmic burning rate is equal to pi r dt. I just write this equation and let us solve this equation. Let us say I do two sets of experiments. I have at temperature T1 the burn rate is R1, at temperature T2 the burn rate is R2, and I am interested in finding out the burn rate at a temperature T2, and therefore I just integrate out this. I get ln R2 minus ln R1 is equal to pi r into T2 minus T1. Ln R2 minus ln R1 is ln of R2 by R1 is equal to pi r into T2 minus T1, or rather I get R2 by R1 is equal to exponential of or e to the power of pi r into T2 minus T1. Therefore, if I know the burn rate at temperature T1, using the value of the temperature sensitivity factor, I can find out the burn rate at a temperature T2, and this is how the effect of variations of temperature is taken into account. I think we are now in a position to go back to designing solid rockets. That means essentially find out how much area is required. But before I do that, let us go back and see, are there any concerns we have about the burn rate equation, because we are going to left and right use the value of burn rate in, let us say, millimeters per second or meters per second given by A p to the power n. What is the unit for R? We say yes, meters per second. If the burn rate is low, millimeters per second. If the burning rate is fast, maybe centimeters per second. This is burn rate, right? Linear burn rate. We illustrated it by having something like a propellant, and we found that it keeps regressing, and the rate of regression is the burn rate. What is the unit of pressure here? Could be Pascal, right? Let us say it will reflect Pascal, could be megapascal, could be atmosphere. Then what is the unit for A? The constant, which depends on temperature, which depends on composition. The unit is becomes a very clumsy. It becomes something like meter per second unit of A, meter per second divided by, let us say, Pascal, fundamental unit, to the power n. And this is not a correct way of doing something, right? you have a unit which is a constant, which is a function of the parameters or the units what I use here, and it is a, I cannot say that my constant is so much meters per second to the power 0.3, 0.32 and all that, it becomes little difficult to use. Therefore, how do I get over this problem? Because the anyway St. Robert's law and we derived this form of equation is found to be true. How do I get over this problem? Well, if I can find the burn rate, let us say I use a temperature or a pressure I call as reference pressure, and I evaluate the burn rate R reference at this particular value A into P reference to the power n, and then I say I am interested in burn rate R at A up pressure to the power n. Then I can write the value of R now as equal to A, instead of A I put R reference into P by P reference to the power n, and this is one way I get over it. In other words, the exponent what I have could be the burn rate at a given reference pressure, provided the reference pressure is used for non-dimensionalizing the value of pressure, and this is how the burn rate is expressed through a non-dimensional pressure which is based on the reference pressure, and this reference pressure is normally taken as 70 atmospheres. You remember when we did nozzle, we said under sea level condition, when you evaluate the specific impulse, or under vacuum we took the chamber pressure as 70 atmospheres, because that is the normal pressure at which a solid rocket, a good performing solid rocket works, or this is equal to 7 MPa, and therefore the burn rate law can now be written as R is equal to R at 70 bar or 70 atmospheres into pressure divided by 70, provided P is in atmosphere, to the power n, or if I am expressing in terms of megapascal, R at 7 megapascal, P is in megapascal, 7 megapascal to the power n. This is at 7 megapascal, same as 70, and therefore many books write the value of R as R is equal to A70, they say this is your reference at 70 into P divided by 70 to the power n. You must remember immediately this we are talking of atmospheric pressure. Therefore, question is, what is A70? A70 is the burn rate at the reference pressure of 70 bar. This is all about burn rates, effect of temperature, but there are many more problems which maybe I think I will postpone it slightly. Like for instance, in a rocket chamber there could be velocity, there could be erosion, there could be external heat flux, those things maybe I will come back a little later, but let us go back and finish this portion on how do I go about designing a solid propellant rocket, and that is the thrust of what I want to do today. But we have already told the answer, right? To get a particular thrust, all what I want to find out is the evaluation of the burning surface area. Let us do a simple problem and then go to something which by which I can evolve for a given thrust. Let us consider a propellant block which is contained in a motor case, and this is what we said constitutes a solid propellant rocket, and here I put insulation. I put a nozzle here. Well, I have a solid propellant rocket as it is. Now, this particular propellant block is ignited over here and it burns from the end. That means the end of the propellant is ignited, we call it as end burning, because it burns from the end. It does not burn from here because this is prevented from burning, it cannot burn from this side, it is prevented, the flame can go normally only in this particular direction. Now, supposing the throat area of the nozzle is 80 What is the value of pressure over here? We have already done it, equilibrium pressure, and that is equal to, let us write it down, rho p A C star S b divided by A t to the power 1 over 1 minus n. Once I know the equilibrium pressure for a given value of S b, I know the value of burn rate R is equal to A p to the power n. I know the burn rate, and therefore, if my grain has, or the solid propellant end burning grain has a length L, the time over which the motor burns is equal to P is constant because the S b is a constant, P is a constant, and therefore, T b is equal to the value of L divided by the length of the grain divided by the burn rate R, which is equal to L divided by, I have A p to the power n. That means the thrust developed by this particular rocket, I know the value of pressure, and the thrust developed is equal to Cf p into At, right. But what do I find? If I want a thrust, and we said solid propellant rockets are generally used wherein you want large thrust as booster stages. Suppose I want thrust of several thousand tons, then in that case S b must be huge, it will be several kilometers, and I cannot have solid propellant rockets whose diameter is going to be extremely large. What is it I am telling? We find that the thrust of an end burning charge, as it were, is going as burning surface area to the power 1 minus 1 by n. If my thrust is going to be large, S b is going to be large, well, I need something like a large diameter rocket which I cannot really carry forward. Therefore, to be able to get some meaningful values, well, why not I try some innovations in this? I have the propellant block, the same propellant block I take, and maybe what I do is, instead of burning it from the end, I burn it radially. In other words, I make a hole in the propellant block, I again put it in the motor case, this is my nozzle, and now this is my propellant block here. I coat the propellant block here with some material which is an insulator which will prevent it from burning on this side. We call it as something which inhibits burning, inhibitor. I coat it with a substance which will prevent the propellant from burning here. Then what I do, I ignite this surface area, the inside surface area, both these areas, and then we told ourselves, if I take a cross section now, what is it I get? I get maybe this is the outer surface, I have the case over here, and then I have the inner diameter over here, and this is my propellant. I take a cross section here, I ignite this internal surface of the propellant, and the propellant burns. We said normal to the surface, it burns radially out, and this type of burning is known as radial burning. Let me illustrate this. I thought I want to get into a little more complicated areas. All what we said is, here I have something like a, let us say, a propellant block like this. This burns from this side, therefore it gets consumed as it goes on. This we say is end burning. The same thing, the same area I take, I house it in a slightly larger diameter. Maybe I take this, I put it inside over here, and now I have the annular area between the outer and inner, which is propellant, and now I ignite the surface area of this particular one, and then what happens is the burning will progress. Let us say normal, I put it over here, I have the annular surface area, and the burning will progress normal to the surface area going like this, and therefore now I have the initial burning surface area, if I were to write for this expression, let us write it down. I will use this part of the board. What did I have? This is my area. I have the inner area here, the propellant block like this. This is my length. All what I am saying is I have this one. All what I am telling is the annulus between the inner and the outer is what is getting burnt. This I say has diameter di, outer diameter is do, and the length of the propellant grain is r. Now, how does the burning take place? It takes place like this, normal. In other words, burning proceeds and then I have thing burning over here. Therefore, what is my pressure over here? The initial burning surface area I have to calculate first. Initial burning surface area is equal to, you could now tell me, is equal to pi di, which is the perimeter, into L, and what is the final burning surface area? Is equal to pi do into the perimeter, and therefore, the pressure equilibrium to begin with Pi is equal to pi dl into, again I have carry over Sp A C star divided by At to the power 1 by 1 minus n. That means I am housing this in a nozzle. The throat area is equal to At over here, right. What is the change we have made? Now I have the entire length, the pi d of it is burning, and therefore I have a much greater burning surface area, and therefore a radial burning grain which burns in this particular direction, I can get Sb to be much larger than in an end burning grain, and therefore I can get a large value of thrust. This is one modification I can do. But there is some limit to it, even if I have an area like this, I cannot, I still need to have a particular diameter and a length. Is it possible to increase this area even further? In other words, all what I am asking is, this represents my initial burning surface area for a radial burning grain. Is it possible to increase this surface area by some means? How can I do? If I can wrinkle these surfaces, I can wrinkle it in some form. And how do I wrinkle it? I try to make a small model. Maybe this was my original perimeter over here. I wrinkle the surface, I make stars on the inner surface. In other words, instead of having something like a cylinder over here, I make the inner surface in the form of a star. Now I find, well, the star, this is something like a 5 vertices are there, 5 vertex star, and therefore now I find my surface area has increased enormously, and therefore now I must be able to evaluate how the burning surface will evolve as it continues to burn. In other words, this is my outer diameter, the outer diameter will come over here and the burning surface will evolve along these surfaces, and this is the problem which we must do. But however, before doing this problem, let us do the simple problem of maybe a radial burning grain burning from inside to outside. What is the value of pressure and what is the time required for burning this? Because in the case of end burning, what did we get? We got T was equal to length divided by APN. We knew how to calculate the pressure, I knew the time taken to burn it. Can I do the same thing for a radial burning cylindrical grain? Let us do that, and let us also find out how the pressure will change. Well, I have the initial value of pressure is equal to whatever I have written there. Let us rewrite it, pi the di, which is the initial perimeter, L is the initial burning surface area, A rho p into C star divided by At to the power 1 by 1 minus n, right. Now, what is the final value of pressure when the burning has progressed? In other words, the burning progresses from the inner cylinder and reaches the outer cylinder. what is the value? The final value of burning surface area is going to be pi dO is the perimeter into L is the final burning surface area, A rho P C star divided by AT to the power of 1 divided by 1 minus N. Now, is the pressure constant like in an end burning motor, or is it a variable now? How would you look at it? That means, dI has increased to dO. In other words, if I were to now plot the pressure, and what is the pressure? Initially the diameter is dI, the motor burns out till the diameter dO is reached. Let's keep our terminologies very clear. This is the inner surface, it is over here. In between the two I have an annulus, it starts burning from the inner diameter, reaches the outer diameter. When the diameter is di, the pressure is pi. When the diameter dO is the final pressure PO, and therefore I know that di is very much less than dO or less than dO. Therefore initially the pressure is this, let us say. When it reaches the final value, pressure could be higher, therefore the pressure increases. Whereas in the end burning grain, what did we have? We found at all values we had the same pressure versus, let us say now the time or the distance, let us say time, I had a constant pressure. Is this all right? If this is all right, now I will ask myself one last question. If instead of having the grain start burning at the inner diameter and progressively burn to the outer diameter, I somehow put the case over here, I ignite the outer surface and then the flame propagates inward, then what is going to happen to me? I am going to get just the opposite. I am going to get the pressure as a function. Now dO gets ignited, then it gradually the flame comes and comes to the inner part. That means I start with a value of P final, that means the initial value is now higher, the value is higher, the pressure drops. In other words, while the end burning grain gave me a constant pressure and therefore a constant thrust, a radial grain burning from inside to outside gave a progressive increase in pressure or a progressive increase in thrust, while inward burning, that means burning from outside to inside, gave me a falling pressure and therefore a falling thrust. Therefore I could have three types of thrust evolution in such rockets, and therefore this is known as neutral burning. What should be the name for this? Progressively increases, that is progressive burning. And thus it keeps decreasing, that means regressive burning. Therefore, all what we have been telling in the last couple of minutes is, well, if I have a propellant which burns from end to end, that means axial burning, well, the type of burning is neutral, constant pressure, constant thrust. If it is burning from radially from inside to the outside, the pressure keeps increasing, while if it burns from outside to inside, well, it could be regressive. Therefore, we could think in terms of three types of burning: neutral burning rockets, solid propellant rockets, progressive burning rockets and regressive burning rockets. Is it clear? If this is clear, question is, what type of burning do you require? See, I cannot say I am making a rocket which is regressive, it is going to fly. Mission will demand something, and what will mission demand? When the rocket takes up, the thrust must be high, and as it goes up the thrust can come down. Therefore, maybe something like this might be better than this, because when the rocket goes up its mass is higher, I cannot expect it to go with a higher acceleration at the beginning itself. Therefore, we have to somehow get balance what type of burning is required for a given system, and that is where when we go into some shapes, when we give these shapes to the internal, that is what did I do here? We just took the inner surface, we just wrinkled it. I could have wrinkled it in any shape. Why should I have to give a star? Star is one of the shapes. I could have wrinkled it into some other shape instead of giving a shape like a star over here. I could have given something like this. I could have given whatever shape I want, and all what I have to calculate is how does the burning rate evolve around this surface. Can I find out how SB changes with time, and once I know how SB changes with time, I know how the pressure changes with time, and I will find out how the force or the thrust which the rocket will develop with time is known to me, and that is all what we do while designing solid propellant rockets. Therefore, to be able to do this, let us do a simple example today. Let us find out the time taken for a cylindrical grain. What do I say by a cylindrical grain? The first example, I have the end like this, I make a hole here, I have internal burning, it burns through like this. The diameter is, let us say, di as what I have written here, the outer diameter is do, the length is L. Mind you, I am repeating this figure. Question is, can I predict how the pressure will change with time, and how do I do it? Well, it is a simple problem. Well, let's do it in a minute. Let us say I have the outer diameter here, do. Here this is the initial diameter which we get started with, di. Let us consider a small part of the propellant gets burnt, and let the small part be of thickness delta over a time, let us say T delta, and then at the end of T delta I will calculate the pressure again, at the end of again 2 delta I will calculate the pressure again, like that I can progressively calculate. And how do I do it? Well, I know that the pressure to begin with, Pi, is this value. What is the pressure at the end? Instead of Pi, I say what is the value at when the grain has reached this, it has started burning from inside, it has come to this level, what is the value of P delta? I want to use this equation and write it. Can you tell me? Well, I say pi. What is the value of d when the thickness burnt is delta? Yes, di plus 2 delta into, I carry these things, others are all constant, A, burn rate constant, rho p, C star divided by throat area to the power 1 by 1 minus n. That means I know the value of pressure at this point, I know the value of pressure at this point. I want to know the time taken for delta of the propellant to get consumed. Therefore, the mean pressure between this and this is equal to P is equal to Pi plus P at delta divided by 2, and therefore, the burn rate, the mean burn rate between the initiation to the, that is from di to di plus 2 delta, is equal to r bar, mean value, and what is that mean value equal to? A Pi to the power n plus A P delta to the power n divided by 2. R1 is the burning rate at the initial condition. It has progressed by a factor delta, in which case this becomes my pressure, therefore, the burn rate has gone up divided by 2, and therefore, the time taken to burn a small quantity between di to di plus 2 delta is called as d delta is equal to delta divided by r bar. Okay. Now, I do the same thing. I now take this as the initial condition. I go to the next step. I find the value of T consumed. I get the value of T consumed, and then I can put the whole thing together and say, as a function of time, my pressure increases from Pi. I know all the intermediate values. I know the final pressure is Pf, which is given over here, and this is how the pressure evolves in an inner burning rocket. We can do this, but this is a numerical way of doing this, there is no other way of doing, and this is the way to do a problem, because when I have more complex configuration, like what I said, I wrinkle the inner surface, I get all these shapes, I can find out how the surface should evolve with time. And this is how one calculates the variation in pressure with time. Once I know the variation in pressure with time, I can readily go ahead and say that the thrust characteristic with respect to time will also change in this particular way. This is how a solid propellant rocket involving radial grain is made. Let's do one more small problem. Supposing I am asked to find out the time taken to burn a propellant, to burn a radial. Now I am using a slightly radial grain between di to outer diameter, the length of the grain being L. The same problem, the same thing what I am considering, the initial diameter is di, the final diameter is do, the length is L of the grain. I want to find the time taken to burn this. I do exactly the same thing, there is nothing more to do, it's again I consider a section over here, the initial diameter is di, outer diameter is do. Why not do a simple thing, like what we say is, let us consider any diameter d. Let us find out the time taken for the diameter d in between di and do to increase from the value d to a value d plus a small change over here, and this I say the diameter has increased to d plus a small amount dd. If I can find the time taken to burn this part, I can integrate out between this and find the time taken, and that is what I will be doing. Let us do that. How do I do it? How do I get the time taken to burn a distance dd? Well, I know that this distance dd is very small, therefore the pressure could be the value at d, and therefore the pressure is equal to we again write it SB is equal to pi d perimeter into length is the burning surface area into rho p a c star divided by AT to the power 1 by 1 minus n. Therefore, what is the burning rate? R is equal to A p to the power n. Now I substitute the value, instead of p I substitute this value over here, I get this becomes this one, let us write it again, pi dl rho p a c star by AT to the power n by 1 minus n is the burn rate when it is here. What is the time taken to burn a small distance dd? Time taken, let us say dt is equal to diameter has increased from d to d plus dd, therefore this thickness is equal to dd divided by 2, that is the spatial length, divided by r, which is the time taken. Okay. And what is this come out to be? Now I find pi is a constant, length is a constant, d is variable, rho p is a constant, all these are variables except n. Therefore, I can write this as equal to dd divided by 2 divided by, I take all the constants to the power n minus 1 as let us say a, and then I have this a over here, and then I write it as d to the power n by 1 minus n. Please let us check if it is all right. All what we are telling is this has units of length, say meters divided by meter per second, this is the time taken, you have dd by 2 is the distance propagated through a small distance dd by 2 divided by a into I club all the factors other than this in terms of a over here, whereas a is equal to pi L rho p a c start by a t to the power n by 1 minus n, that is a, into d, because a variable, into n by 1 minus n. I have to integrate out, and what is it I have to integrate? The time taken to burn from here to here, it is at 0. Let us say the time taken to burn is Tb, time taken for burning, b, small b denoting the burn time. Therefore, I get dt goes from start to the end, which is the burn time, which must be now equal to, as it goes from initial diameter to the outer diameter, and the value of variation is dd divided by 2 divided by d to the power n by n minus 1, and I can take a and a outside, which is equal to 1 by a into a, because these are all constants. All right. Now, what do I get on integration? I get Tb minus 0, therefore, Tb is equal to 1 over 2 a into the exponent of the burning rate law. Now, I integrated d to the power, that is n d to the power, I get, if I bring it up, it is d to the power minus n divided by n minus 1, therefore, this becomes 1 minus n by n minus 1. Is it all right? I had d over here, I brought it d n minus 1, I take it up, it is d minus n by n minus 1, and therefore, integrate out, I must also get divided by 1 minus n by minus 1. Was it n minus 1 or 1 minus n? 1 minus n, 1 minus n, 1 minus n, 1 minus n. What is the final value therefore? This is equal to 1 by 2 a into 1 minus 2 n divided by 1 minus n, that means 1 minus n divided by 1 minus 2 n in the denominator, I am sorry, into dO to the power 1 minus 2 n divided by 1 minus n minus di into 1 minus 2 n divided by 1 minus n. This is the time taken for the burning rate. It is possible to have a closed form expression, and this is the value. Please check whether there are any mistakes in this. Therefore, we are able to find out the burn time, but now I will ask you a question. If n is equal to 0.5, what is the time for burning? We said as long as n is less than 1, it is all right for us. If n is equal to 0.5, what will be the value of burn time? Let us do it. 1 minus 1 is 0. So, there is a problem. That means this why is it not usable? Can we ask ourselves what has gone wrong? We have done it correctly, but it is not working at n is equal to 0.5. Why? Can somebody come out with an answer? Well, this seems to be the problem, and how do I do this problem? I think we should be able to analyze it. Let us go backward. Our integral is dt or Tb is equal to, let me write that, 1 over a into integral di to do of what? dd by 2 divided by d to the power 0.5 divided by 0.5, and therefore, it is equal to dd, that means I will take 2 over here, and this gives me, for n is equal to 0.5, I get 2a ln of dO by di. That means what happens for 0.5 I need to use a ln form, because the point is when I substitute this I will not be able to get for n is equal to 0.5, and similarly if n is equal to 1 I get all erratic things, and we found n is equal to 1 is not possible. We are able to get all the solutions under the limiting cases, and this is how a cylindrical grain will be designed. Therefore, what is it we have done in today's class? We looked at the effect of temperature on burn rate. We also defined the value of A as A70 at a reference pressure of 70 bar. Then we learned how to develop an equation for thrust and pressure for an end burning grain. We also did for a radial burning grain, but we found for radial burning grain the pressure evolution had to be done by in increments, while the burning time we could solve using this particular equation. I continue with this in the next class, and in the next class we will do something little bit more. We will look at the evolution of burning surface area from something like a star grain, maybe n types of vortices, and also look at different forms of grain shapes which are used in practice and the reasons for it. After that we will summarize the whole thing on solid propellant rockets by incorporating maybe the igniter and other aspects into the solid propellant rockets, right. Well, thank you then.